Alright guys, so last week we talked a little bit about how to name alkanes and talked a little bit about the structure and how to draw them and things like that. And so today what we're going to talk about is what does the structure actually look like, how does that influence a little bit of the behavior, and then what are some special things about alkanes and really about organic molecules as a whole that we'll need throughout the rest of the semester. They're going to be different from some of the molecules that we might have learned about in Chem 1. So let's jump right into it. First off, and I know that water obviously is not a molecule that is an organic molecule that we talk about, but to go into the behavior of some of the alkanes and some of our organic molecules as a whole, it's helpful to remember that water is weird, right? I mean, water is a polar molecule because it's got this really strong, it's got this really strong electronegative atom. It's bonded to hydrogen atoms. If you recall from your Chem 1 classes, that sets up this thing called hydrogen bonding, right, where we've got another water over here, and really, I mean, we're talking, trillions of them, but that they're sort of loosely bonded together, and I'm doing a bad job of drawing those dots there. And that really strong intermolecular force there that we have with water leads water to behave really oddly, right? I mean, it sticks together a lot, it has a really high boiling point, it's got cohesion, adhesion, capillary action, surface tension, all of those things that make water really unique and really useful to us as far as the biochem side of things that we'll get to next semester. Alkanes, on the other hand, don't have that at all. I mean, alkanes, what we've got in the case of our alkanes is we've got these carbon-hydrogen bonds for the most part, right? I mean, of course, yeah, we've got some carbon-carbon bonds too, but mostly carbon-hydrogen bonds. They're pretty much purely covalent. I mean, they're not completely nonpolar. I mean, they're not identical, but they might as well be for most of our purposes. And what that means is that they don't exhibit the same characteristics that water does. They don't stick together very well, and so that's going to change really all of their properties. The first thing that matters for us is, I mean, it means that they're going to be insoluble in water. So if we put some gasoline, say, into some water, what does it do? It floats on top, right? Because they don't mix. And even if we shook them up together, they're going to separate back out. Think of vinaigrette salad dressing, the same sort of deal. The vinegar is moderately polar, and obviously the oil is completely nonpolar. It's much like an organic molecule. And so you can shake them together, and they'll sort of stay together, and then as soon as you sort of set it down, they're going to separate back out. We also would term that as immiscible. They don't mix together. But what it means for us is that we can't dissolve alkanes in water. It doesn't mean they can't be dissolved. They can, just not by water. They would have to be dissolved by non-polar things, because remember, our general rule for whether or not something dissolves is like dissolves like. That's our thumb rule, our rule of thumb, which says that non-polar things dissolve non-polar things, and polar things dissolve polar or ionic things. So water dissolves a lot of ionic stuff and polar stuff, but it doesn't do a very good job of dissolving things like alkanes and hydrocarbons. Remember that since we don't have hydrogen bonding because we don't have a lot of electronegativity, that really the only kind of intermolecular attraction that we have in alkanes are something called van der Waals attractions, and specifically we get a lot of London dispersion forces. And remember that the way that works is, since this is a relatively nonpolar bond most of the time, the only way that we can get it to act dipolar, which is what we need for intermolecular forces, is that the electrons are moving around in the bond here. The bond obviously, remember, is two shared electrons. And sometimes, instead of the electrons being evenly distributed like this, sometimes they're on the same side of the molecule. So like in this case, if the two electrons were here, and this is just for an instant, we're talking about, femtoseconds. This isn't happening for very long. But for just a moment, there's a negative side over here, and there's a positive side over here. And that little tiny bit, that momentary attraction between the different molecules as they get just a slight instantaneous polarity, is going to be enough to hold them together just a little bit. Not very much. And again, this is obviously going to mean that the boiling point of these substances is going to be way less. So methane, which is a molecule that's pretty close to the size of water, molar mass of 16 compared to the molar mass of 18 of water, has a boiling point of something like a negative 167 degrees Celsius, whereas water has a boiling point of 100 degrees Celsius. And that is that is pretty much entirely due to those really massive intermolecular forces in water, and the really tiny intermolecular forces in these alkanes. All right, so that leads us to this idea here that alkanes in general are going to have much lower boiling points than most other organic compounds. In almost all of our other organic compounds, not all, but in most of them, we've got more than just carbons and hydrogens. And if we've got more than carbons and hydrogens, our chances for polarity tends to go up. And so you're going to tend to have a little bit more intermolecular attraction. Alkanes don't have much at all. Now, the way this does work, though, is that the boiling point is going to get bigger as the molecule gets larger. So like methane obviously has a really low boiling point, and say decane is going to have a much higher one. And you can kind of tell that. I mean, methane is natural gas, and once you start to get up to butane and higher in the chains, they're liquid at room temperature. And so that obviously shows you that the boiling point is much higher for those bigger chains. As we branch the chains, their boiling point is actually going to decrease, and we'll talk a little bit more in class and look at the structure of that and see why that is. But essentially, I mean, they're going to have less attractions because there's less chance for some of that polarity to happen when the chains tend to get a little bit more branched. Okay, so remember those couple of things. Just remember, alkanes are going to tend to have lower boiling points. All right, let's get down into some of the structural oddities that we're going to talk about in organic chem that we didn't really talk about in regular chem last year. The first one is that if we've got a molecule, and real quick, hold on, I had a structure built, but let me pop this off and change it a little bit. If we've got a really simple alkane here, like ethane, okay, and this is the stuff that we've been working with in class, okay, C2H6. If we've got single bonds here, we can rotate around those single bonds. Now, we say here in the notes that it's free rotation, and there ain't nothing free in science. There's still energy costs associated with that. But that means that we can actually rotate this molecule a little bit. And so we could have it sitting like this, okay? Or we could rotate it around that single bond between the carbons a little bit, and we could get some different arrangements. Those two arrangements, and actually there's really an infinite number of arrangements, as we talked about in class, those are called conformations, or sometimes called conformers of each other. At room temperature, it doesn't really matter a whole lot for us. It's really, you can't really separate them out very well at room temperature, but as you decrease the temperature, you can start to pull these things apart. They're going to behave a little bit differently, and some of them are more stable than others. So how does that work? Well, this is our ethane, right? And these are the couple of ways that we could draw it. And these are the ways that, remember that obviously if I just said, you know, at the beginning of the year last year, I said, hey, draw a C2H6, we would have just said, okay, awesome, and you would have drawn your H's, and I know I can't draw H's. This is the killer for organic chem for us, is that I can't draw H's on the tablet. That would be our C2H6, but of course that would indicate that it was pretty much flat, and we know that that's not the case. We've talked about that in previous units, and so we're going to use a couple of models to show that that's not the case. We could use our dash wedge module. Okay, remember wedge goes back into the board essentially. The dash part, I'm sorry, goes in, and the wedge part comes out. So that shows that three-dimensionality of it. Okay, so you got these two hydrogens up here are in the plane. These are coming out at you guys, and that's the dash part. And then these two in the back here are the wedges that are basically coming back at me. This little model here is called the Sawhorse Model. Just another way to represent it and just sort of show that there's some three-dimensionality to it. And of course, there's a couple of different ways that we could draw these things, and these go along with the different conformations. But in general, the way that we want to draw conformations, the way that we really want to see that rotational structure and how that works, is we're going to use these things called Newman projections. So these Newman projections, what you do, essentially, is you take your molecule like your ethane, and you're going to look right down its barrel, like you're looking right at it right there. And then you're going to be able to see the molecules that way. So if you're looking at this one right here, this essentially corresponds, let me move it a little quicker, this corresponds to this Eclipse model right here. In other words, I've essentially got all the molecules sort of lined up nice and symmetrically, and so I can't really see this back row back here, okay, because the front row right there is in front of it, okay? So that's one conformation. We could also turn that, and we could have what's called a staggered conformation, where it sort of looks like an asterisk or a star, okay? And in that case, these back ones we can actually see pretty clearly, even though the front ones are there. Now, obviously, there's an infinite number of conformations that we could do, but in general, something like this, we're going to talk about just a couple of conformations. And so we've got the Eclipse model, where you can't see the back molecules, and then we've got the staggered one, where you actually can, okay? And this is how we would draw them. And I know that sometimes students struggle with this, so the circle there doesn't really mean anything other than just to sort of orient everything in place. Draw your little sort of Mercedes symbol here, okay? The front one, the one that are actually attached to the Mercedes symbol, that is these ones up front, okay? So these are the Mercedes symbol. And then the back ones are going to be the other sort of triad there that you can't actually see. Now some of you may be saying, well, where the heck is the carbon? Well, the carbon is actually there. The carbon is right there. In fact, both of the carbons are there because we're looking straight down the barrel of both of those carbons in this ethane. Okay? So that sort of shows us what those look like. So what does that actually mean? How do I know, where to put all of that stuff, and how would I draw another molecule maybe that looked like that? Well, the conformations aren't all as stable as, each other. So if we look at, if we look at those two conformations again, if we look at our Eclipse conformation like that, okay, and then we look at this conformation, what we actually see is that the staggered conformation is actually going to be much more favorable. In other words, it's going to be much more likely for us to see the staggered conformation right here than it is to see the Eclipse conformation. And the reason behind that has to do with energy considerations. And really, the easiest way that I like to think about it is it really has a lot to do with space considerations. If these things are eclipsed like this, and then we sort of turn this, these two hydrogens up here, remember they have these big electron clouds going around them? And what that does is that those electron clouds are sort of interfering with each other. Remember our Vesper theory, electron clouds don't like each other. Whereas if I turn this, okay, to the staggered model, sorry, trying to get in front of the camera, then what happens is that this is now not interfering with one here. These are sort of offset, and so they don't run into each other. So that takes much less energy to occur. To cause it to turn into the eclipse formation costs energy. And remember, we don't like to cost energy if we can avoid it. General rule in chemistry is that most of the time we try to shoot for the lower energy formation. Okay, so when you're asked a question about which one of those conformations is going to be more stable, you want to sort of do a three-dimensional analysis there, or build a structure if you can, and then figure out which way can I keep stuff as far away from each other as possible. So to look at that in a more complicated sense, this is a butane, okay, and if we're going to look at the conformations of butane, okay, so here's your molecule up here, C4H10, right? Okay, and this is what the eclipsed formation of it would look like sideways, and then if we looked at it from the Newman projection way, it looks like this, okay? And what you should sort of see when I turn it back sideways, though, is that these methyl groups up here, the ends of the butane, they are just running into each other, okay? They don't really want to be with each other. Even if I twist them a little bit, I mean, there's still obviously going to be a massive amount of overlap there between the molecules, and that's just not good. We don't want that to happen. So what that means is that the eclipsed formation like this is going to be relatively unstable. And so what would work a lot better is, how about if we twist this a little bit, okay, and go to a staggered formation. So in other words, if I took my molecule and I sort of twisted that single bond in the middle, well, now that definitely looks a lot better, right? Because now I've still got a little bit of overlap here, but not near as much. The pressure, when you look at it on the sides there, is going to be much less. What you can also imagine is that what would actually make it a lot less is that if we completely rotate it around, this is called an anti-formation, okay, and you guys don't really necessarily need to know that, but if I had the butane sort of all out in a line like that, well then this methyl group is way away from this methyl group. They're not interfering with each other at all, so that's a really stable formation, really low energy situation. Again, we can still exist in the other formations. We can exist in that eclipsed formation, but pretty unstable. I mean, that molecule is not going to want to do that. We can also exist in that staggered formation over there that's called the Gauche Formation, where we're about 60 degrees offset, okay? And we could also exist, obviously, at 120, okay? We could exist at 180, and again, really anything in between. But where you're going to tend to find these things is what's the lowest energy. So butane molecule, sort of the way that we drew it up initially, right? It's going to be like a nice long chain like that where they're sort of avoiding each other. And that's one of the reasons why when we draw these skeletal structures, we draw them in these angles like this so that they stay as far apart from each other as possible. All right, guys, hopefully that helps you out a little bit with conformations. And obviously we'll do some work in class and get some practice on drawing these and figuring out which ones are most stable. Thanks a lot.